just some details of the schedule while we're waiting for other people to come in. But Madison, I wanted to ask you first, so because I forgot what your schedule is. So what's going on this week in terms of review sessions?
Oh, so I had a regular review yesterday from
Mhm.
12 to 1, and then I'll be having my exam review tomorrow from 12 to 2, so 2 hour long session.
Oh, okay. So tomorrow from 12 to 2. So have you posted that in Blackboard?
Yes, I posted it in, I've edited my times on my little folder, and so I
Uh-huh.
have that available. My Zoom ID and passcode are the same for my exam review as
Mhm.
well.
Okay.
Mhm.
When you posted that, did you send an email? Did you send that announcement as an email, or do we need to do that?
I'll go ahead and do that after this class.
Okay. All right. So
Mhm.
that's great. So there will be an exam. Do you have anything on Thursday, or are you using the test review to replace your Thursday session?
I'm using the exam review to replace my Thursday
Okay,
session.
that's fine. All right. So
But
12 to 2.
yeah,
So
I
I
should
hope
say that.
everyone heard Madison. So 12 to 2 tomorrow at her regular location on Zoom. Madison will be having a lengthy 2 hour test review. So Madison, um, you probably already saw the emails, but so the solutions to the test review are posted. I posted those Friday, and then when I was making the video for the test review, I found a couple of corrections. So they're pretty minor. So I corrected a couple of things and then reposted that on Sunday. So the correct version is now posted of the solutions to the test review. And so that's a really good thing, a really good tool to use. This homework on that was due today, but I shifted it back till midnight Wednesday, is also very good. This is pretty comprehensive, has lots of questions like the test review you'll see when you're going through this homework. So this is also a good thing to use as a reference for preparing for the test on Thursday. All right. This homework, this is a new homework that I just posted over the weekend. Notice I have that due on Thursday, March the 4th. This has only got 3 questions on it. And there's really no computation on this homework. This is just interpreting instantaneous rates of change, giving interpretations for instantaneous rates of change. And so this is also a really good assignment to finish before you take the test. So it's very short. This one, though, problems on this homework will not be covered on the test, but this one is good to look at also before the test. I've put on all of the prior homework so far. I've posted the answers. So if you go back to one of the prior homeworks and open your prior homework, it will show the correct answers to every question. Is with the question now. So you can look back through your prior homeworks also if there were certain questions from prior homeworks that you didn't understand. The correct answers are now available for all the prior homeworks. So, but not this one or this one since those are not due yet, right? So, okay. What I was just saying there about the test is so that's going to be Thursday, right? We will have class on Thursday. So there will be class on Thursday, and then the test number 1 will be posted immediately after class. So at 1:15, it will be posted in the test and answers folder on the Blackboard page. So if you go to the Blackboard page, you go to the test and answers folder. That's where the test will be posted. And then so be sure to come to class on Thursday because we're going to do new material on Thursday. But then immediately after that, you can look at the test. And it's due back to me at 1:15 on Saturday. So you have 2 days to take the test. So what you will do is, of course, open the test. You can write your answers you can print a copy of the test and write your answers on the test. that's fine. Or you can, if you don't have access to a printer, that's fine. Also, you can just look at the test online and then just write down your answers on a separate sheet of paper, okay? So you don't have to write on the test paper. However,
you said it's supposed to be PDF, right?
yes, so whatever you write on, whatever paper you write on, again, remember, you have to convert that back to PDF. So you have to scan that to PDF, either with a scanner or with your phone using an app, and then send that back to me in PDF form by 1:15 Thursday, and email it back to me just at my regular email address, which is here. It's wallerw@uhd.edu. Be sure you email to this address. Do not send it to me as a Blackboard message, because that's not going to work as well. So just email it to me as an attachment back to this email address, and I will confirm when I get it from you. I will send an email back to you saying I have received it, and so I'm ready to grade it. But by 1:15, so you have 48 hours, right, to get that back to me. So some of you have already know. Oh, so now let me show you before we go on. Well, let me just mention here quickly. There's I did tape discussion of some of the solutions, not all the solutions, but some of the solutions to some of the review problems, some of the key ones. And so I posted that video. It's there along where the test sample is, okay? And where the solutions are. Actually, we'll see that now, because I'm going to switch here. If I can make this work, I'll switch to Blackboard. And here's Blackboard. And my version of Blackboard, I guess yours kind of looks the same. So here's where the test will be posted. And there's, of course, where the sample test is. And that's where now the solutions to the sample test are posted in this folder. And that's where that link to that video is, also in this folder. Now, I wanted to point out that when you go to the test folder, of course, the test isn't there yet. It'll be there at 1:15 on Thursday. But there are these instructions posted for how to convert your written test to PDF, and then of course you know how to email that back to me. But how to convert it to PDF, you can use an app on your phone, and there are many such apps, and a few of them are mentioned in these instructions. Okay, so be sure to look at these instructions before you get ready to submit the test. Give yourself a little bit of time. If you're thinking, this is going to be difficult for you, give yourself some time to, get this process done. So you'll be ready to email that back to me by 1:15 on Saturday. Okay. All right. So I just wanted to point that document out to you. And then if you, again, in the sample tests, you go to that folder, there's the answers to the sample test already posted. And then there's that link to that video where I'm just going through some of those solutions. And then Madison will also go through those solutions as well and answer, your questions maybe a little bit more thoroughly than I can on a video, right? And then also that final homework here. Well, these final two homeworks that are on the test, okay? The one due tomorrow, and then the one due Thursday at midnight. But again, remember, this one's very short. Okay, so do y'all have any quick questions there? So that's what's going to happen on Thursday, but we do have class, so you can ask me questions again in class if you're having
we're scanning it
questions. Yeah, Colin. So you will you can print the test if you're able to, and you can write your answers on the test, or you can write your answers on a separate sheet of paper, but that needs to be scanned to PDF to get back to me, right? So do not take a photograph of it. You can take a photograph of it in order to convert it to PDF, but do not send me the photograph file. So don't send me a JPEG file, right? Don't send me that because that's hard for me to work with. What?
Do you want the work or anything? Or just the answers?
Yeah, so be sure you read the instructions on the test. So there are instructions at the top of the test, and it says convert this to PDF and email it back to me, all of that stuff I just said. But it also says make sure you show your work, make sure you show enough work to justify your answers, make sure you follow the instructions, right? Okay, make sure you follow the instructions. Sometimes the instructions will say things like interpret or explain or justify. If that instruction is given with a problem, you must include the explanation or the interpretation or the justification. That must be included. So you cannot skip that, because that will cost you points. That could in fact cost you all of the points. And make sure you show enough work to justify your answer. And the advantage to that is, well, there's an advantage to me. I need to see your work, but the advantage to you is I can give you partial credit in that instance, right? So if you make a small mistake, you know, won't lose all the points for that.
How neat does it need to be?
So it is definitely show your work. Go ahead.
Sorry, I didn't mean to interrupt, but how neat does it need to be?
All right, so okay, so the instruction says neatness is important. So you should try to be neat. You know, you have to make it so I can read it because you know, I'm going to be grading it, and I won't have you you know, to ask questions of when I'm grading it. So you know, make sure you think that I can read it, right? Now, how much detail do you need? Again, that's a little bit subjective. I just said enough work to justify your answer. So if there is something that you needed to write down, right, to arrive at the final answer, make sure that you include that, okay? So if you didn't need to write something down, then it's not really, probably would not expect to see that, so I won't be you know, counting off for that. But if there's an important step that I know that any normal person, and I'm assuming everyone in the class is just a normal person, would have to write something down to, you know, get through that step, I'm going to expect to see that, right? So I'm not, I don't mean to insult anyone in the class, but I'm assuming that we're not Einsteins. I'm certainly not, and all of us have to write down stuff, right? Okay, other questions there?
Nope.
Okay, so that's the way it works. Again, give yourself a little bit of time to scan it, right? If you haven't done that before. And again, there are kind of generic app instructions for doing that in that document that says how to scan and submit tests. But of course, if you start running into difficulties at the last minute on Saturday, you can try to contact me, right? So you can try to email me and say, I'm having problems. Might be able to help you. Okay, there is two problems actually in this homework that I wanted to look at because I forgot to mention this last time. So, so let me open this and go to those problems. So this is this instantaneous rate of change homework. So it's due tomorrow. And this is really very good for the test because the problems on this homework are many of them are very similar to the review questions you'll see. And so they're really good practice for the test. So if you get through this homework really well and go through the review really well, then you know you're really well poised for getting a good score on the test.
Which homework was this one?
What now?
Which homework was this one, or is it a new one?
No, this is computing and interpreting. No, I'm sorry, I forgot what the name of this one was. Measuring change or instantaneous rate of change.
Oh, okay, the current one. Oh, okay.
That's the current one, right? So due tomorrow. Now, so if you down here on problem 11, it says a graphing calculator is recommended. Okay, so I wanted to mention that if you have a graphing calculator, then that's cool. You can use that. But if you don't have a graphing calculator, you can use Desmos, the tool that I use in class for graphing. It's very easy to use. And I wanted to show you that there's a link to that. There's a link to that tool right here at the top of the homework under instructions. You see right there, you might also open the description if you want to, but in the instructions, see that link that says basic function graphing? If you click on that, that will take you to a Desmos screen where you can graph a function, okay? So just click on that and it will open the Desmos screen for graphing a function. Here's the screen that you're going to see, in fact, or something very close to this. Okay, so the instruction just says enter a function formula graph. So here you would just enter the function formula, right? You would just type that in. To get the exponent, use the caret symbol on your keyboard, and that will give you, which is the shift of the 6th key, right? And that will give you the a chance to type in an exponent. I thought that formula was going to be x cubed. What is that in the homework? I thought that formula was going to be x cubed minus, where's that homework? I thought that was going to be x cubed minus 5x, but it turned out to be different than what I expected. Where is that? Oh, here it is. Okay, so they changed that up on me, and this version of the problem, it's x cubed minus 2x. All right, so all you would do is just type in x cubed minus 2x, right? That's what f of x is, and then over here on the right hand side, of course, as you've seen throughout the class, right? Desmos will make a nice graph of that function if you've typed the formula in properly. Okay, so here's a graph of x cubed minus 2x. And then you can use that graph, right, I think, to answer the questions, answer the parts of this particular question. Now, of course, sometimes when you make a graph, you may need to adjust the graphing window. So the graphing window means the portion of the x and y axis that you're looking at in the graph, right? In Desmos, you can, it gives you a standard graphing window, which is something like this one, -5 to 5 on the x-axis and -10 to 10 on the y-axis. Of course, you can zoom in, right? If that's one way to change the graphing window. You can zoom out to change the graphing window. So you can hit the plus minus icons here over on the right-hand side. But if you hit the wrench key, it will open up a settings box, and you can actually change the portion of the x-axis you're looking at and the portion of the y-axis that you're looking at. So you can adjust the graphing window more carefully, right? Okay, so here where it says x-axis, you can put the smallest value you want to see on the x-axis and the largest value you want to see on the x-axis, then also the smallest value you want to see on the y-axis and the largest value you want to see on the y-axis. And so you can adjust the graphing window very specifically. And sometimes you'll have to do that, if the function is a little bit unusual, right? Okay, so let's see. So what do we think the answers are here in this particular case? Well, let's see what the questions are. So what did it ask us? It wants us to find the local minimum and maximum values, right? Okay, so that should be easy to do by looking at the graph. And then once we get these written down, it wants us to say where the function is increasing and where the function is decreasing, right? Well, once you've located the minimum, local minimum and local maximum values, then it's pretty easy to answer where it's increasing and where it's decreasing. By the way, in WebAssign, they want you to enter the local minimum and the local maximum as coordinates for points, right? So watch for that. You'll enter both the x and the y coordinate, where the local maximum and the local minimum is. All right, so let's see in WebAssign where we think that is, right? I'm sorry, let's look in Desmos and see where we think that is. Well, this obviously is the local maximum. So if you point at that, Desmos is very friendly, and so it really gives you what the coordinates of those the points are. So it's what, minus 0.816 and 1.089. Okay, let's write that down. So minus 0.816 and 1.089. That's the local maximum, and then right here is local minimum. So that looks like 0.816. And minus 0.1089. So it's sort of symmetric there, right? For the local minimum. And now it's very easy to see, right, where the curve is increasing, where it's decreasing. It's increasing up to this local maximum, decreasing between the local maximum and the local minimum, and then increasing again after this local minimum, right? Shall I try typing those values in? We can try maybe one of them there and see if I can get it right. See if I can find my keyboard here to type with. So let's see, what was the X coordinate there? Minus 0.816. Oh, does it give me instructions for how many decimal places I'm supposed to use? So you have to follow that. Oh, just 2 decimal places, right? So that would be minus 0.82 for the X coordinate, and then the Y coordinate was what, 1.089. So that's 1.09 if I round that off to 2 decimal places. Oops, yeah, that's the maximum. Okay, so let's submit that and hopefully we got it right. Yay, okay, so that's pretty easy, right, with that graphing tool. So that's what I wanted to point out to you, right? If you don't have a graphing calculator, that's fine. In that case, on those homeworks where you have to do some graphing, I will try to include, again, this link at the top of the homework. It'll either be under instructions or description, this link to where you can do graphing. Let's try also the next one, because that one is terrible. The next one I meant is problem number 13. Okay, all right. So definitely need a graphing calculator here. So what this formula tells you is the, well, what does it tell you? The volume in cubic centimeters of 1 kilogram of water at temperature is given by this particular formula. Okay, this is for temperatures between 0 and 0 degrees centigrade, so that's freezing, and then 30 degrees centigrade, right? Okay, and so you have a really nasty formula here, right? In this case, and you want to find at which temperature between 0 and 30, right? The volume is going to be at a minimum. So here we have kind of a chemistry question, right? Okay, so between 0 and 30 degrees centigrade, when is the volume of 1 kilogram of water, when is that at a minimum? So so this is really just a local minimum question in disguise here, right? In the context of chemistry in this case. So from a mathematical point of view, all we have to do is graph this function, right? And look for the local minimum. Well, graphing is easier said than done since this formula is kind of ugly, right? But again, with Desmos, it's not really all that bad. So again, you would just use the graphing tool, right? Okay, type in the formula and then try to adjust the graphing window so you can answer that question, where's the local minimum? I've already got this one typed in, so let me open it. So here is the graph of that formula. By the way, notice I changed variables here, and so you can do this in Desmos. The t was the input variable in the problem, right? See, it says t, but I changed that to x just to make it friendlier for Desmos. And the v is the output variable. I changed that to y, okay? Because, you know, our standard output variable is y and not v. So I typed in the formula like this using y and x. And then to see the graph, I had to adjust the graphing window. So notice I'm using from 0 to 30 on the x-axis as my x graphing window. And then I really had to adjust the y graphing window so I could see this graph. And so notice I'm going from what, 998 up to 1006 here, okay? So that took some work to find this graphing window. And again, you can adjust the graphing window here using the wrench settings. Well, where is that local minimum? I think it's right around here, isn't it? Well, there's what Desmos says that it's pointing it to me, okay? So there's the local minimum. So that local minimum occurred at x equals 3.967, okay? Right? So at a temperature of 3.967 centigrade, that's when the volume is the smallest. And so I think that's what we would give as the answer back here. Let me try typing that in. So find the keyboard again here. So 3.967. So rounding that off to 2 decimal places, is that what they want? Yeah. So 3.97. By the way, on the test, unless I say otherwise, and I don't think I did on the test, you can always sort of default to 2 decimal places as kind of a good, if you have to give estimated answers, 2 decimal places is enough accuracy for us. Let's try submitting this. Now, when I looked at this earlier, okay, graded it right. Good, that's great. Okay. Actually, WebAssign gave the answer as 3.96, but I think the correct answer, but they graded this correctly anyway. I think the right answer is what Desmos gives, which is 3.97. Okay. So conceptually, those are easy problems, right? But the difficult part of the problems is doing the graphing. Okay, so y'all have any other questions that you want to ask about that?
Can we do question number 3? We have that in the review, but like this one, I try to use the same method as you used on that question.
Okay,
but
so
it
what is,
didn't work.
all right, so question number 3. All right, so yeah, so they're giving us this, the black curve is the curve that they're interested in, right? Okay, so there's the function that we're graphing, and it says estimate the slope of the graph at these 2 points. So the 2 points that are plotted here, correct? Here, this one is x1, y1, and this one is x2, y2, right? Okay, so slope again is a concept that is really reserved for straight lines, correct? So when you're talking about slope of a curve, you're really using the term slope incorrectly, right? Because slope is something for straight lines, right? But the way we adapt that concept of slope to curves, right, is we say the slope of a curve at a particular point is the slope of the tangent line at that point, okay? And that slope of that tangent line is also called other things. It's also called the instantaneous rate of change at the point, and also the derivative at the point, right? Okay, so slope, instantaneous rate of change, derivative, those are all interchangeable terms. So we're trying to find the instantaneous rate of change or the slope of the tangent line at this point. Well, that means we have to see the tangent line, correct? And they have very conveniently for us drawn in the tangent line, okay? Daniel, they've drawn in the tangent line. So there's the tangent line. It's a nice flat line, and so we really don't have to do any work here, because what is the what's the slope of flat lines, horizontal line? 0, right? So the answer here is going to be easy. That's going to be 0, right? Okay. So slope of a curve is at a particular point is the slope of the tangent line at that point. But to calculate that slope, right, you've got to be able to see the tangent line. So that's really the problem that we're going to be working on today is, how do we find these darn tangent lines, right? Fortunately here it was drawn for us, but what do we do when, it's not drawn for us? So at this one, at this point, right, again, the tangent line has been very nicely drawn in here. So we have to calculate the slope of this blue line. That just means we have to find 2 points on the line and apply the slope formula. So you're going to have to look along this line and find 2 points that you think are on this line, correct? Okay, can y'all, wow. Can you find 2 points that are, we want to find points that are really very close to the line. So
the ones that I had used was 0.0 for the x2 and y2. And then the second point I had used 1.5 and 1.
So you said 1.5 and 1 is on the blue line?
Yes.
So
and I got the right answer.
So here's 1.5, and then up here at 1. Yeah, that looks pretty close. Yeah, Yoselin, I think you're right there. That point looks like it's pretty close to being on the line. And then what else did you use?
0.0, which was the X2 and the Y2 line already drawn.
So
I mean, not 0, 1 and 0.
Oh, okay. So you used so you used this point right here.
Yes.
And so you estimated its coordinates to be, of course, the Y coordinate is 0 because that's sitting right on the X axis. So the Y coordinate is 0. And then you said the X coordinate is 1.
Yes.
Yeah. I would say that's slightly different though from 1. So you got the right answer though. So it's pretty forgiving. But I would have probably put like 0.9 there or something.
I thought about it, but I went for it and I got the answer of 2.
Okay, all right. So you took the easy choice there and you wound up getting it right. Okay, all right, that's good. I would probably try 0.9 and 0 and then just calculate the slope between those 2 points. So Yoselin says 1.5 and 1 and 0.9 and 0. If I sort of do that, I'm doing in this off on the side here, calculating the slope. I get 0 minus 1 in the numerator. That's the difference in the Y coordinates. And then 0.9 minus 1.5 as the difference in the X coordinates. So I get minus 1 over minus 0.6 and whatever minus 1 over minus 0.6 is. Okay, so 1 divided by 0.6. 1.67 or something like that. Did you get close to that also?
Well, since I used 1 instead of 0.9, I had got 2.
Oh, okay. So, you got 2. All right. So let me try this one. Let's see if it, so it may, wonder what it may not like my answer then.
Nice.
Yeah, that counted it right. So it's being very forgiving in how we choose points there. Okay, and I'm pretty forgiving too when I know you're estimating the slope of a tangent line. Okay, and you're having to pick points off of the line. I can tell if you're doing it properly, even if you may come up with a slightly different answer than what I came up with. Daniel, does that make sense?
Yeah, that makes sense. I get it now.
Okay, all right, good. So this might be kind of a typical type question for the exam. Okay. All right. Other sorts of things there. So again, the questions here all are really good. You know, like questions like these, you know, where they give you points. They want to know, is the instantaneous rate of change positive or negative or 0? Are these tangent lines or not, right? The tangent lines that are drawn on this curve, are those really tangent lines, or are those not tangent lines, or could they be tangent lines? These are sorts of questions that you'll see on the review, and then they're likely to be on the, also likely to be on the test, okay? All right, so so much for that homework. Let's go back now to our notes, and so let me see if I can find the notes. And so last time we had well, sort of you know, we're going through the things that we just did on that homework, right? We were talking about tangent lines and their relationship to instantaneous rate of change. Okay, all right. So so let's do another example here, and sort of go through this whole process of computing an instantaneous rate of change using the tools that we know at the moment. Okay, so this example says the graph of this function x cubed minus 5x is shown here. Okay, and then we're going to use that to answer some questions. So that graph is right here. Okay, when I say shown here, it's actually down a little bit. All right. So let's start going through the questions. Some of them are straightforward. Well, the first one is straightforward anyway. So it says find f of -2. Well, that's not even a calculus question, right? That's an algebra question. So f of -2 is just doing a little bit of arithmetic, right? So f of -2 is going to be -2 cubed minus 5 times -2. And so -2 cubed is -8, and then we would have +10. So that comes out to be 2. So we know the point -2 and 2 will be on the graph of this function, right? Okay. And indeed, that's correct. If you look at the graph of the function, here's the graph of the function, and see the graph goes through the point -2 and 2. Now, what we're trying to do here, though, ultimately is to find the slope of the curve here at x equals -2, right? Or again, that's the same as finding the instantaneous rate of change of the function at -2, or you could say find the derivative of the function at -2. Okay, so that's our goal here, is to do that, right? And so to find the instantaneous rate of change at -2, we need to have a tangent line. And so last time we were doing that by using Desmos and zooming in on the curve, right, close to x equals -2 until the curve appeared to be a straight line, right? And then we were computing the slope of that quote unquote straight line that we were looking at, and we were using that as the slope of the tangent line. But now suppose that we don't have Desmos available to us, we only have this graph available to us, and we want to find the tangent line. So we're not able to zoom in on the graph until the graph looks like a straight line. Well, in that case, we have to just draw the tangent line ourselves. All right. So we're just going to have to by hand physically draw in this. We're just going to have to draw in this tangent line. So that's what I've done here on this graph. Okay, is the best I could. Just eyeballing it, I drew in the tangent line. So if you look at the review, there's at least one problem, maybe two problems, where you're asked to yourself draw a tangent line. Okay, and so that's a good thing to practice before the exam. Is try yourself, just given a graph of a function and a particular point. Remember, tangent lines apply to just particular points on the curve. Different points have different tangent lines. So if you have a graph of a function, pick a point and see if you can by hand draw what you think is a convincing tangent line to the curve at that particular point. So here's what I've drawn as the tangent line at -2. So I think if I were to zoom in on this point, if I were able to zoom in on this point really, really closely, this black tangent line and the red curve would coincide. They would duplicate one another. That's what I think. Y'all think I did okay there? Y'all scared to say it's horrible or something?
No, I was just trying to understand. So a tangent line, when we make them, it just kind of goes along to what it's doing. Like if the line is increasing, we just kind of make a straighter line.
That's right. Again, you're thinking about if I zoomed in on this point of the red graph, right? If I zoomed on that point, if I zoomed in close enough, I would just see a straight line, right? So I'm just trying to extend that line up and down. So I think that close to this point, the red graph looks like the black line. That's what a tangent line is. So it's the line that duplicates a curve close to, the close to is really important, close to a particular point, Jocelyn. So I think what you said was correct. Yeah.
That makes sense. Thank you.
Right. Okay. This is my approximation for the tangent line, but you might have, so different people are going to draw slightly different tangent lines. And so they'll get slightly different estimates for slopes of tangent lines and slopes of curves and instantaneous rates of change, therefore, right? Okay. So, I've graded enough papers to know when you've done it properly or when you really made a horrendous mistake. Okay.
How would you know
in
that
doing
if it's correct or not?
what now?
How would you know if it's correct or not?
Yeah, that's what I was saying. I will know if you have done it correctly. Okay.
Is there any way that we could check ourselves to see if we've done it?
Not currently. There's
Okay.
not. Okay.
I understand
When
what
we
you're
get
saying.
more sophisticated at how to find tangent lines, then it'll be easier for us to check it. But currently, you just have to wait until I post an answer, and if your answer looks like mine, then or close to mine, it doesn't have to be duplicate. But if it's close, then you've done it right. Okay. Okay. So now what I would do here is once I had drawn what I think is a tangent line at a particular point, then I need to calculate the slope of that tangent line, right? So that means I have to pick 2 points off the tangent line. That also is sometimes a little bit tricky. Obviously, one point that will be on the tangent line will be this point itself, which we know its coordinates are -2 and 2, right? But then we have to find another point on the tangent line. So you just have to pick off another point that you think is that looks like it's on the tangent line, okay? Just like Jocelyn, you did in that previous problem, okay? I looked at this point because I thought I could figure out what the coordinates for that point were. That point is on the line, right? And its coordinates are kind of easy to figure out. Let's see, the x coordinate is going to be -3. See, this is -1, -2, -3. So the x coordinate is -3, and then the y coordinate is not quite as clear, but it's -1, -2, -3, -4, -4.5. So -4.5 is my estimate for the y coordinate for this point. But you may have picked a point up here, right? You don't have to pick this point, just some point off of the line and try to estimate its coordinates as best you can. And once you've got the estimate, for the coordinates, right, then you just use the slope formula, correct? So from this point on, it's all very straightforward. So my slope formula would be what? Difference in the y coordinates, right? So that's -4.5 -2, -4.5 -2 divided by the difference in the x coordinates, right? So that's -3 minus a -2. -3 minus a -2. So we end up here with -6.5 over -1, because this is going to be -3 plus 2 in the denominator. And so that reduces to 6.5. So there is there's my answer. I think the slope of the curve right here at -2 is 6.5. So let's fill that in. So there we drew the tangent line. Our estimate for the slope of the tangent line was 6.5. And that's the same as instantaneous rate of change. So the instantaneous rate of change, remember our notation for that is the prime notation, right? So you would write f prime of -2 is equal to, or approximately equal to, 6.5. So see, that's actually kind of a fun process because you get to draw the tangent line. Now I want to tell you that I happen to know, and you will soon figure out how I know this. I happen to know that f prime of -2 is exactly, not approximately, it's exactly equal to 7. So if we could draw the tangent line perfectly and compute its slope, we would get 7. So I actually drew a pretty good tangent line there. My estimate is pretty close to correct. It's only off by a half. So I'm pretty pleased by that. You can draw pretty good tangent lines by hand, okay? And get pretty good estimates for instantaneous rates of change by hand. You can get surprisingly close that way, okay? But I just happen to know that this is and you will soon figure out why this is the exact value for the tangent line. Okay, let's try that again. All right, so notice in this part E, we're asked to estimate, and then we have to interpret. So the interpretation is kind of the same as interpretation for slope, but we have to start with the estimate first. So we want to estimate f prime of 1. That's not the same as f of 1. Okay, all right. So be careful that you're. See if I can get my pen to write again. So remember, there's a big difference, right, between f of 1 and f prime of 1. F of 1 means what's the y value that matches the input of 1. That's easy to compute. You just use the formula. F prime of 1 means what's the instantaneous rate of change, or what is the slope of the graph at the input 1, right? Okay, so kind of a completely different idea. Here is the point on the graph that corresponds to x equal 1. So it's at the point 1, -4. So f of 1, I didn't, apparently when I plug 1 into the formula, I get the matching y value is -4, okay? But now the more interesting question to us in calculus is, what is the instantaneous rate of change at 1? What is the slope of the graph at 1? And to find that exactly, we need the tangent line, right? By the way, before we actually calculate this, before we actually estimate this, is this going to turn out to be positive, or is it going to be negative? So is f prime of 1, is that greater than 0, or is that less than 0? You can figure that out without even doing any calculations. Which is correct there? Is it positive or is it negative? Or maybe it's exactly 0.
Positive.
Which one?
Positive.
Damien, you say positive. Why did you say positive?
Oh, wait, no, negative. Okay. Oh, I was just thinking of 1's greater than 0.
You're thinking, oh,
Yeah,
1's greater than
I
0.
messed up on that.
Yeah, 1 is greater than 0. That's true. Okay, right. But we're interested in f prime of 1, right? So what about f prime of 1?
It would be a positive. I would.
So you're saying the rate of change, the rate of change, or the instantaneous rate of change is positive? So remember, rate of change is how are the y values changing when x increases, right? So when you're at this point, when x is increasing, see, when x is getting larger at this point, what's happening to the y values? The y values are going what?
Down.
Down. So that means the rate of change has got to be negative, right? Does that make sense?
Yeah.
Yeah. So so we know, without doing any calculations, we can roughly figure out that f prime of 1 is negative, right? Because the curve is decreasing. So this is an important thing to remember, right? Where a curve is increasing, any place where a curve is increasing, the rate of change is positive. Any place where a curve is decreasing, the rate of change is negative. So at 1, since the curve was decreasing, the rate of change we know has to be negative. How negative is it? That's what we want to calculate. So we actually want to give a value for it, but we can see that it must be negative. What happens when the rate of change is exactly 0, neither positive or negative? What's happening on the graph then, Damien?
Could you repeat the question again?
Yeah, so I said where the curve is increasing, the instantaneous rate of change is positive. Where the curve is decreasing, the instantaneous rate of change is negative. Well, what if the instantaneous rate of change is 0, which is neither positive nor negative? What's happening on the curve where the instantaneous rate of change is 0?
It's staying the same, I want to say.
Yeah, it's staying the same. Okay. Well, curves don't stay the same very long. So can you sort of think about what staying the same means?
It's remaining 0.
Yeah, it would be a turning point, Damien, like this.
Okay.
Right. Does that make sense geometrically?
Yeah, no, it does.
Yeah, right. Okay. So yeah. So where the rate of change is 0, then, which is neither positive nor negative. This thing is making me crazy. Neither positive nor negative, then that's where you have turning points. That's going to be a real important clue to us in the future, because we're often looking for turning points. Turning points are really useful to us. And so we'll be looking for turning points by looking for where the rate of change is 0. Okay. All right. Well, now let's get back to this question, though, before we take a break. So I want y'all to quickly for me, you've got to look at the graph here. So, I moved the graph. So, man, I did a bad thing. All right. I see if I can move that back. I may have messed up the problem. Yeah, let me see if I can do this with the.
What if you press the undo
That's
button
better.
a couple times?
Okay. All right. So there we go. That looks a little bit better now. All right. So before we leave here, let's finish the problem. So we actually wanted to estimate the instantaneous rate of change right here, right at 1 and -4. Okay. So what we have to do is find the slope of this tangent line, right? So I've drawn in the tangent line, and so what I want you to do is calculate the slope. So y'all have to pick off 2 points on that tangent line and compute the slope for me. So you're going to have to squint there to see if you can find 2 points on the tangent line. One of them is kind of obvious, right? It's one of them is kind of obvious here at 1 and -4, right? That has to be on the tangent line. So see if you can pick off another point. See if you can pick off another point on this tangent line so you can calculate the slope, right? Okay. So just do your best there to get an estimate for that.
2 and -2.
So yeah, so just everyone will write down something slightly different. So so y'all do that, and then so take a couple of minutes, just pick a point on the tangent line. Don't have to pick it perfectly, and then calculate the slope with that point, and then obviously this point, right, which must be on the tangent line. So take about another minute there. I'm going to see if I can find someone who I have not called on. So if I haven't called on you and you're hanging around, then you're going to help me answer this for the class. See if I can find it. Who's here? Most everyone who's here has already answered for me. Okay, yeah, I don't see anybody who has not already answered a question, so let's just discuss it. Did y'all find a point? Someone want to share their other point?
Would 0 and -2 be one?
0 and -2. There's 0, but I don't quite see it at -2. So there's 0 on the x-axis, but that's not quite -2. Here's -2 right there, right? Okay, but that's fine. what is that? Let's estimate what that is on the y-axis. So it's not quite -2, because -2 would be here. So what does that look like, Lewis, to you? What's a little bit better estimate for that?
About like 1.8, 1.9.
Yeah, something like
Negative
that, right?
1.8.
So maybe minus 1, it's minus, right? So maybe minus
Correct.
1.8, okay? Yeah, so that would be a good estimate. And then we just have to calculate the slope, right? So we get, let's do this right. So -4, this y coordinate minus this one. So minus a 1.8. And then, well, that's really sloppy. And then the difference in the x coordinates, which is easy, that's 1 minus 0. So the denominator here is 1. So I just had to figure out what the numerator is. So that's -4 plus 1.8, right? Which looks like -2.2. So I come up with -2.2, all right, as our estimate for the slope of this curve at x equals 1, or the instantaneous rate of change at x equals 1, or the derivative at x equals 1. Did y'all also get the rest of the class get something like this? Something close to this? Give or take a few decimal points?
Mm-hmm.
Anybody get something wildly different? All right, so so there it is. There, f prime of 1 is minus 2.2. Okay. All right. So now what is the interpretation of this? Okay. So this is hard to interpret because it's not in context. But you would say at x equals 1, right? Y is decreasing. Y is decreasing because this number is negative by 2.2 units, or you could just say 2.2 when x increases by 1. So it's very much like the interpretation of slope, right? In fact, it is the interpretation of slope because instantaneous rate of change is the slope of the tangent line, right? So, but be sure you say at x equals 1, okay? Because at other x values, this is not true. But at x equals 1, y is decreasing by 2.2 when x increases by 1. Don't say y is decreasing by minus 2.2, because if you're decreasing by a negative amount, that means you're increasing, right? So the sign is already taken into account by using the term decreasing. Okay, so any questions there before we proceed? Okay, so look, what we're having to do, right, to find instantaneous rates of change is we're having to find tangent lines. So one way we found tangent lines is by zooming in on a curve until it looks like a line, right? That requires us to have a calculator or a computer. If we don't have the calculator or computer and we have the graph, we can still draw the tangent line by hand, right? And then estimate the slope of the tangent line. And that allows us to find instantaneous rates of change, okay? But that's a little bit unsatisfying because we know these are only estimates and different people will come up with different estimates. So what we want to do is see if we can make this process exact. Can we exactly find the tangent line and its slope to a curve at a particular point? So how do we make this process more exact? Well, that's what we're going to take up here in just a minute, right after the break. All right, so it's 12:30 now, so let's take 5 minutes, and then we'll come back, and I'm going to show you how. Well, we're going to start learning how to exactly find instantaneous rates of change without having to use a calculator, okay, or a computer, just from the formula for a function that we're given. Okay, so we're going to take the estimate out of this and learn how to do this analytically. That means by hand, exactly. Okay, all right. So let's pause there, and I'll see y'all in a few minutes. Okay. Hope everyone's back. All right, now, okay, we're gonna do something now that will really kind of blow your mind. All right, so this is a really fun thing that we're getting ready to do. So you're really getting ready to learn differential calculus now. All right, so let me start off with an example though. Just to, so this is another example of finding an instantaneous rate of change, but now we have a problem in context. So this might make it more interesting. So this says the water depth, which we're calling Y, this is measured in meters, of a narrow channel that's going to vary as the tide goes in and out, right? So it varies with the tide T elapsed hours after midnight. All right. So the T here is going to be the input variable in this formula, and that stands for elapsed hours after midnight. Okay. So 6 would be 6 a.m., right? Or 9 would be 9 a.m. All right, so we can calculate that depth according to this formula. This is a sinusoidal function. There's a fancy term for you, sinusoidal function. And the reason it's a sinusoidal function is because it involves a trig function. In this case, it involves cosine. So even though it's cosine in the formula, this is still called a sinusoidal function. So you see this is kind of a nasty formula here, right? 3.1 times the cosine of 0.52 times t minus 2. And then we have to add on here at the end this shift of 8.5. Okay. All right, so that's the function that we're working with, right? And so the first question is very easy. It just says find f of 7, and what does f of 7 mean? So this is not a calculus question. It is a kind of a hard question though, because you have to evaluate this sinusoidal function. So that means you have to plug the 7 in for t, right, in this formula. So when you do that, you get this big expression, 3.5 times the cosine of 0.52 times 7 minus 2, and then plus the 8.5. And so you really need a calculator to help you evaluate that. Make sure you've got your calculator in radian mode though, okay? So make sure the calculator is in radian mode, because we're gonna evaluate this cosine in radians. And when you do that, this comes out to be 5.84, right? So of course, what that means is that 7 hours after midnight, in other words, at 7 a.m. in the morning, the depth of that channel is 5.84 meters, all right? Okay, so that's just plain old f of 7. Now, what we want to do, though, of course, is figure out what is f prime of 7, right? Okay, so we know what f of 7 is. That's 5.84. So at 7 a.m., the channel is 5.84 meters deep, right? But next, we want to do the calculus part of this, which is calculate f prime of 7. And that means at what rate is the depth changing at 7 a.m., right? So the depth is 5.84 meters, but how is the depth changing at 7 a.m.? That is what the instantaneous rate of change tells us, okay? So the only way we know to do this so far, right, is to either make a graph and zoom in on the graph, or draw a graph of the function and try to draw the tangent line here at x equals 7. All right, well, that's what I tried to do here. So here is the graph. Notice this is a sinusoidal curve, right? So it is periodic. So no, it's got this nice wave in it, right? This nice sinusoidal wave, because of course, the depth of the channel is going up and down, right? As the tide comes in and out, okay? So, so here's what's happening at 7 a.m., right? The depth is 5.84, right? And so we can immediately deduce, right, that f prime of 7, is that positive or is that negative? Okay, so who was answering that before? F prime of 7, is that positive or is that negative? just from looking at the red curve, right? What's f prime of 7 going to be? What's its sign going to be?
Is it negative?
Yeah, Lewis, it's negative. Why would you say negative?
I was just thinking because the way the curve is going.
The way the curve is going, what is the way the curve is going at 7?
It's decreasing.
It's decreasing, right? So when the curve is decreasing, right, that means that the instantaneous rate of change is negative, right? And so in Lewis, you can see that better when you try to sketch in the tangent line here, right? You can see that better when you try to sketch in the tangent line because the slope of the tangent line is negative, right? If you draw the tangent line right here, you get a line that has negative slope. And so obviously the slope of the tangent line is negative. That means the instantaneous rate of change is negative. By the way, Lewis, what's happening? What's the rate of change going to be over here at 8, by the way? There's 8. So without even doing any work, Lewis, you are already going to know what's f prime of 8 going to be.
Positive, because it's changing upwards.
I don't think it's changing upwards there. Okay.
Oh, it's zero, like it just stays the same.
Right? Yeah, f prime of 8 is going to be 0. Yeah. Okay. See here, if you draw a tangent line, you're going to get a flat line, right? And flat lines have slope 0. So remember at turning points, Lewis, in this case, this is a local minimum. Remember at turning points, the rate of change is 0. Okay, right?
Correct.
Now over here at some time over here, like at 10, for instance, at this point, the rate of change is going to be positive, right? Because this is where the curve is going up, correct? Okay, all right. Now, so all we can do right now to figure out exactly what f prime of 7 is, we know it's negative, but that's not a very good estimate, right? If we want to get a better estimate, we would pick another point off of the curve, right? I'm sorry, pick another point off of the tangent line that we've drawn. So I've drawn a tangent line here. I think that's an okay tangent line. Some of y'all might not like that, actually. Anyway, that's my tangent line that I've drawn right there. And so you pick another point off of the tangent line, then you calculate the slope, right, Lewis? Okay, Lewis, so you have to do something for me here, but keep it a secret, all right? Okay, so let's estimate the instantaneous rate of change. So I picked this point right here as on the tangent line, because I thought I could figure out what its coordinates are. Let me see if I can figure out what its coordinates are, because it's on a grid point there, right? This point right here. So let's see. The x coordinate for that point, or in this case, the t coordinate for that point is going to be, this is 2.5. So the first coordinate is 2.5. And then the second coordinate is, this is 5. So this would be 6, 7, 8, 9. Whoops. Put the parentheses too soon. So there we go. All right. So there's another point on the tangent line. And now I can calculate the slope of the tangent line. So Lewis, I want you to do that for me. Calculate the slope between these 2 points. Okay. 2.5
Okay.
and 9 and 7 and 5.84. Will you do that for me, Lewis?
Yes.
Yeah. But don't tell the class. All right. Just write that down on somewhere on a sheet of paper, and I'm going to refer back to you in just a minute. Okay. All right. Okay. So Lewis secretly knows what my estimate for the tangent line, and therefore Lewis has the estimate for the instantaneous rate of change at 7. Okay. So we'll leave that as a question mark. Okay. But again, this is only an estimate. All right. So I want to find a way of calculating this slope of this tangent line exactly. Okay. So where I don't have to go through this messy process, this clumsy process of drawing the tangent line and trying to pick points off of the tangent line. Correct. Okay. All right. So that's my goal here. All right. So I'm going to switch notes now, and let's talk about how we can do this a little bit more methodically. So this is exactly the same example. I still want to calculate f prime of 7. All right. Now let me show you the way we're going to do this, okay? And at first I am going to use Desmos, okay? Right, I am going to use Desmos, but we're going to go through a process here that even though I'm using Desmos at first, we're going to go through a process where I will be able to ultimately take the Desmos out of the process. So I'll be able to do the process without having Desmos, okay? But we're going to start with using Desmos as a crutch. All right, so let me switch back to Desmos, if I can find it. And let me find the right example. I hope it's this one. Yes, okay. So let me open this graph. All right, so, well, this graph should look kind of familiar to you because this graph should look kind of familiar to you because this is the, this is just that curve that we were just looking at. All right, so that's the curve that shows the depth of the water in the channel. And there's that point where I'm trying to find the, there's the point now where I'm trying to find the instantaneous rate of change right there at 7 and 5.84. All right, now I need everyone to pay really close attention because this is a really key process now that I'm going to go through, right? So everyone open up your ears here, right? So you're watching what I'm doing. Now, look at what I have drawn here on the curve, all right? This red line, what is this red line called? What sort of line is that? Okay, y'all aren't paying attention because you aren't answering me. What now?
A tangent line?
It's not a tangent line, Calvin, okay? So what kind of line is that though? We don't know that many different types of lines. Oh, so Colin said it. It's a secant line. Yeah, okay. So that's a secant line, right? Okay. So I've drawn a secant line here from t equals 7 up to t equals 12. All right. Now, when you calculate the slope of the secant line here from 7 to 12, when you calculate that slope, you're calculating what type of rate of change. It's not an instantaneous rate of change, but what type of rate of change are we computing when we find the slope of that secant line? We don't really know that many different types of rates of change. So there's instantaneous rate of change. What's the other type of rate of change that we have calculated?
The average
rate of change.
Yeah, right. So what I really found here is if I calculate the slope of this secant line, I found the average rate of change from 7 to 12. Okay. All right. This is what Desmos has calculated for me. So let me show you that calculation. All right. So if you look over here on the left now, we started at the point 7, right? Okay. And we went up to we started at t equals 7 and we went up to t equals 12. Okay. Now, the way I'm going to express the 12 is I'm going to express it as 7 plus a number. So 7 plus what gives you 12? Now, 5, right? Okay. So that number 5, I'm going to refer to as the increment. Okay. So and the reason I'm doing it this way is just to set up the calculation so I can repeat them. Okay. Which is what I'm getting ready to do. All right. So we went from, we calculated here, or Desmos has calculated the average rate of change for me starting at 7 and going up to 7 plus an increment of 5, which is 7 plus 5 is 12. All right. So look over here on the right. We started at 7. Our increment is 5. So that means I'm going to calculate the average rate of change from 7 to 7 plus 5, which is 12. And there is the formula for average rate of change, right? That's just the slope of the secant line. That's f of 7 plus 5, which is 12. Turns out to be 9.952 minus f of 7, which turned out to be 5.844, and then divided by 12 minus 7, okay? 7 plus 5 minus 7, 12 minus 7. So the difference in the horizontal coordinates here, right? And what Desmos came up with is 0.82. All right. So at first that doesn't seem all that exciting or even all that useful, right? Because I was trying to find the instantaneous rate of change at 7. So that's the slope of the tangent line at 7, right? And the slope of that tangent line, I don't think has anything to do with the slope of the secant line, right? Because the secant line doesn't look anything like the tangent line at 7, correct? Okay. All right, but here's what I'm going to do, okay? Now, so by the way, this average rate of change turned out to be 0.82175. Someone write that down for me. Can someone write that down for me? 0.82175, that's plenty of, you can stop at the 5, that's plenty of decimal places, all right? So that was the average rate of change from 7 to 7 plus 5, in other words, 12, all right? In other words, the slope of this secant line. Now, here's what I'm going to do, okay? I'm going to repeat this average rate of change calculation. So I'm going to do this average rate of change again. Of course, if we were doing that by hand, that would be kind of messy, right? Because I'd have to do all this arithmetic. But fortunately, Desmos is doing the arithmetic for me. So I'm going to repeat this average rate of change calculation, but I'm going to change the increment now from, I'm going to change the increment from 5. I'm going to lower it. I'm going to change it down now to 1. So let me type that in. And notice the picture here changes substantially, right? Okay. So we still have a secant line here, right? But now I'm calculating the average rate of change starting at 7 and going over to 7 plus 1, which is 8. And here's what Desmos says that average rate of change is. It's minus 0.44292. Can someone write that down for me? So minus 0.49292. Now, again, that's an average rate of change. That's not an instantaneous rate of change. This is a secant line. This is not a tangent line. But look, that secant line is kind of starting to look more like the tangent line that we're interested in, right? Because we want the tangent line here at 7, okay? And this secant line is kind of looking like what that tangent line would be here at 7. Do y'all agree with that? It's a lot closer than the secant line I drew before, right? Okay, does that secant line kind of, at least it got the right slope, right? Kind of resemble what the tangent line would look like here at 7? Someone say yes or no, or I don't understand what you're saying.
Can you show the other tangent line?
Not tangent line, but secant line.
Oh, okay, secant line.
Yeah, I've only been drawing secant lines here. Okay. Oh. All right. So, well, yeah. Let's do that. Okay. So first, I drew this secant line. Okay. So that secant line from here, that doesn't look like anything like what the tangent line would look at 7, right? See, the tangent line at 7 is going to look something like this, correct? Okay. Right. It's going to go downhill from left to right, maybe along here. But this secant line, that secant line doesn't even have the right slope, right? It's going uphill from left to right. The tangent line here at 7 would be going downhill from left to right, right? Okay. But now what I'm thinking is let's draw an average rate of change, but let's not go from 7 all the way to 12 because 12 is too far away. Let's just go from 7 to 8 and let's draw that secant line. So to calculate that secant line, we would use an increment of 1. That means I'm going from 7 to 7 plus 1, which is 8, right? And what do we get for the slope of this secant line? I get minus 0.44292, okay? All right. And I'm thinking, yeah, that secant line looks more like what a tangent line would look here at 7. Not the same, but looks closer. All right. So did someone write that down for me? Because we need that value here. All right. Now, here's my really key question. How can I make that secant line look even more like the tangent line at 7? So I've got this secant line, this red line, but I want it to look more like what the tangent line would look like at 7. How can I get that? What can I do?
Maybe if you do h equal to 0.5.
Ah, there we go. Okay. So what Saad is suggesting is, let's pull this point even closer to 7, right? Okay. So let's find an average rate of change, not from 7 to 8, but from 7 to something even closer to 7, right? So we do that by lowering the increment. So I'm going to change the increment down. Saad, you said to 0.5. Okay. All right. So there's the secant line from 7 to 7. Here's 7. And going over to here is 7.5. Okay. Notice those 2 points are really kind of close together, right? But that's still a secant line. But that's looking more like the tangent line at 7. All right, let's write down that value, minus 0.64309. Someone write that down for me, okay? All right, Saad. Now, listen, the computer's doing all the work here. So we can continue this process, can't we? So if I want a secant line that's even more like a tangent line, what can I do?
Keep getting closer to 7.
Get even closer to 7. In other words, change the increment again, right, Lewis? So what do you want to change it down to?
0.2.
0.2? Let's try 0.1. Don't be shy here.
Oh, okay.
So you see that? There's the secant line from 7 to 7.1. But since Desmos is doing all the work, let's make the increment even smaller. So let's make it 0.01. Have to get rid of a decimal place here, right? Wow, okay. So there's the secant line from 7 to 7.01. By the way, when you calculate that average rate of change from 7 to 7.01, here's what you get, minus 0.82739. But look, we can keep this process up. Let's go to 0.001. So there's the secant line from 7 to 7.01. There's the calculation of its slope, and we get this number. So here's what the early people in calculus were thinking. They were thinking, well, why stop this process? Okay, I can make this increment smaller and smaller. There I made it 0.001. Wow, okay. Look at that. Desmos is having trouble even distinguishing the points, okay? That is still a secant line, though. That's the secant line from 7 to 7.0001, okay? And that secant line looks almost identical to the tangent line, right? Okay. And what's its slope here? Minus 0.83095. Let's go even further. We can do this as much as we like. Wow. Okay. There now, you really almost cannot distinguish, right, the secant line from the tangent line. Okay. That secant line looks like it should be the tangent line at 7. What's the slope of this secant line? In other words, what's this average rate of change? It's minus 0.83098, right? So here's the idea, right? We can estimate what the slope of the tangent line is going to be, right? By computing slopes of secant lines, right? But by using very, very small increments, right? For that average rate of change for that particular secant line. That's the process that we're going to use here. All right, let's go back to the notes now, because I want to fill in what I just wrote down. What we just did, I want to write it down in my notes. Okay, so what we just did was calculate a bunch of slopes of secant lines. We calculated a bunch of average rates of change. Okay, and so we started first by going from 7 to 12, right? That was an increment of 5. By the way, I'm calling that increment H. That's my favorite variable for the increment. And what did we get when we calculated that first slope of that first secant line, that first average rate of change? Did y'all write that down? So the one from 7 to 12, did someone write that down?
I believe it was 0.82175.
Okay, so all right, so it was positive, right? Okay, 0.82175, which
right.
we know is nothing like the tangent line, right? Because we know the tangent line at 7 has to be negative. All right, now next we calculated an average rate of change with the increment of 1. Okay, and that looked more like the secant line there looked more like the tangent line, right? What did the slope of that secant line turn out to be? Did someone write that one down?
Negative
So the one where we used an increment of 1, what?
0.44292.
So minus what?
44292.
Okay. All right. And then did we write down the one where we used an increment of 0.5? That was where we were going from 7 to 7.5. Did we write that one down? That one turned out
was negative 0.643097.
All right, so something like this, right? 6.4, and then here's the one for 0.1. When we used an increment of 0.1, that was the average rate of change from 7 to 7.1. So I already calculated that one and wrote it down here. That would turned out to be minus 0.79. And then when we used an increment of 0.1, we got minus 0.827. And then we got minus 0.831 when we used an increment of 0.001. And then when we used an increment of 0.0001, we still got minus to 3 decimal places. We still got minus 0.831. Now look, you can continue this process of calculating these average rates of change, right, and drawing these secant lines with smaller and smaller increments. Of course, these secant lines with smaller and smaller increments are going to look more and more like the tangent line. But the slopes of those secant lines, in other words, these average rates of change, notice these are starting to converge to the same number, right? It looks like even if you continue this process, right, and use smaller and smaller increments, it looks like you're going to arrive at what? What are these numbers in our in this far right-hand column? What are they converging to? What do we see? It's all going to come out to be
0.83.
Yeah, minus 0.83, actually minus 0.831, something like that, right? Okay, if we want to go to 3 decimal places. Yeah, so we can continue filling out rows in this table, but it looks like these slopes of these secant lines are moving toward minus 0.831. So that should be the slope of the tangent line, okay? If we think about continuing this process indefinitely, it looks like these average rates of change are going to converge to, are going to move to, get very close to minus 0.831. So that is going to be my estimate here for f prime of 7, okay? But I think now that estimate must be very good, all right? Much better than I could do by drawing the tangent line by hand and picking off 2 points on the tangent line. Okay, Lewis. All right, so Lewis, you did that. You calculated the slope of the tangent line by when we drew the tangent line and we picked 2 points off the tangent line. What did that slope turn out to be?
Not sure if it's right, but it's negative 0.70.
Minus 0.70.
Mm-hmm.
Ah, okay. All right. So so there was our hand estimate, right? Okay, is minus 0.7. But here is our estimate, Lewis, that we know is that must be much more accurate, minus 0.83. Okay, well, these numbers are close to each other, right? Okay, they're not that far apart. So our hand estimate is not too bad, right? But it is somewhat different, right, from our what we think is our very accurate estimate of minus 0.831. All right, so this is the actual process that we're going to use for computing slopes of tangent lines or instantaneous rates of change. All right, now at first this seems very clumsy, okay, because it looks like there's a lot of work involved here, right? Especially if we were trying to do this by hand. All right, but we're going to see that it's not as bad as it appears. All right, let's try this again, however. Okay, so let's look at, we have time for one more example. So I want to find, here's a function. There's no story with this function. So we just have this formula, 4 minus 1/4 x squared, and we want to find the instantaneous rate of change at minus 2. Okay, so here's a picture of this function. It's a pretty easy parabola, 4 minus 1/4 x squared. Here's the input minus 2, and I just drew in the tangent line here, right? Okay, so there's my hand version of the tangent line. So you can see, right, that that what's the sign of this instantaneous rate of change going to be? Is that going to be positive or is it going to be negative?
It's going to be positive.
Positive, right? Because the curve is increasing here at minus 2, right? Okay, now I could go through the process of trying to pick a couple of points off of this tangent line that I drew, and then, you know, of course, this is the point. What is that point? Minus 2 and what is that? 3. Yeah. All right. So we know this point is on the tangent line, and then we can pick another point off of the tangent line and then estimate the instantaneous rate of change that way. Okay. But I would have what could be a fairly rough estimate that way, right? So we want to get a much more exact estimate. So we're going to go through that process again, but now we can do it very quickly, right? With Desmos, we're going to go through that process of drawing secant lines, okay? And drawing secant lines that we know are closer and closer to the what the tangent line looks like, compute the average rate of change as the slope of that secant line, and see what those average rate of changes are converging to, all right? But we can do this now very fast with Desmos. All right, so let me switch back to Desmos. I already have this example, I think, made. So let me see if this is the right example. No, is that the right example? No, that's an old example. So let me see which one is, maybe it's this one. There we go. Okay. All right. So there's that parabola, right? And we want to find the instantaneous rate of change right here at minus 2. Okay. So here I've drawn a secant line already. So this is the secant line that starts at minus 2 and goes over here to 4. So there's the average rate of change from minus 2 to 4. There's the secant line that has negative slope. So that secant line looks nothing like the tangent line that we're interested in, right? Because we want a tangent line with positive slope. Okay, so we're going to fix that by changing this secant line, right? But what increment did I use here starting at minus 2 to get this secant line? Well, I was starting at minus 2 and I went over to 4. That's an increment of 6, right? Because minus 2 plus 6 is 4. So the average rate of change of this function from minus 2 to minus 2 plus 6, in other words, from minus 2 to 4, that turns out to be minus 1/2. So because Desmos did the average rate of change calculation for me. So the slope of this red line is is minus 0.5. Okay, all right, but that red line looks nothing like the correct tangent line. All right, so how do I fix this picture?
Bring it closer to 4.
Right. No, I want the
Oh,
rate
sorry,
of
yeah.
change.
-2.
So bring
-2.
this point closer to -2, right? So how do I do that, Lewis?
You change the H.
Change the H, right? So what do you want to change the H to?
-4 or -2.
No, I can't use a negative. I can't use a negative increment, right? We're always going from -2 plus some number. Okay. So if you want to bring this point back to -2, you would go -2 plus a number smaller than 6, right?
Oh, okay.
So I'm just asking you what do you want to use there? To start
2.
2. All right, so let's do that. So let's go with an increment of 2. That gives me the average rate of change from -2 to -2 plus 2, which is 0, right? So we get this secant line, and that average rate of change turns out to be 1/2. All right, Lewis, so that's close to the tangent line right here, right? But it's still obviously not the correct tangent line. So how do I make this better?
You keep going down.
You keep going down, right? Okay. So what do you want to go down to?
0.01.
Okay. All right. So you want to cut right to the chase there, right? So let me try 0.1 first, though. All right. So there is the secant line from -2 to -2 plus 0.1, which is -1.9. That's already pretty close to the tangent line, right? Okay. Notice the number the average rate of change we're getting is 0.975. So look at that number, 0.975. All right, Lewis, now I'll do what you said. Let's try 0.01. Wow, that really is a secant line, but you almost can't distinguish it from the tangent line, right? And what do you get as the slope of that secant line? 0.9975. Let's keep going. So let me add another 0 here. So you really can't tell this secant line from the tangent line, right? What do you get as the slope of that secant line? 0.9975. So notice we had 0.975, then we had 0.9975, and then now we have 0.9975. Guess what? If I add another 0, what's going to happen? You're going to get what? 0.99975? Yeah, there you are, right? Okay. And that that secant line looks almost exactly like the tangent line. Look what you get for the slope there, 0.99975. So Colin, let me ask you, if I were to, really bore myself by continuing this process all afternoon, and I keep decreasing the increment, and next I use 0.00001, and then I use 0.000001, and then keep adding zeros with a 1, right? We can already predict what this average rate of change is converging to. What's it obviously converging to?
9, all 9s.
Well, all 9s, right? Okay. If you have a string of decimals that are 0.9999999 and you have all 9s, what number do you really have there?
1.
1, right? Yeah. So these are really converging to 1, right? So that must be the correct slope for the tangent line. Okay, it must be 1. Wow, cool, right? So we think the slope of the tangent line here, the instantaneous rate of change, is very close to 1. All right. That is how we're actually going to compute now instantaneous rates of change, by finding secant lines that are converging to tangent lines, and then looking at what the slopes of those secant lines, the numerical slopes of those secant lines, are converging to. Obviously now, though, we cannot always rely on Desmos to do this. So how do we do this without using the computer? Because that sounds like a lot of arithmetic, right? So how do we get rid of that arithmetic? you already know the answer to this question.
Is it
What process do you use to eliminate arithmetic? What in mathematics is one step above arithmetic? After you learn arithmetic in grade school, what do you learn next? What subject? Also begins with an A.
Algebra.
Algebra, that's right. Algebra is going to be the key here, okay? By doing a little bit of algebra, algebra replaces a lot of arithmetic, all right, okay? So by using our algebraic knowledge, that's how we're going to get around all of this arithmetic that appears to be involved in computing all of these slopes of secant lines, okay? All right, so, well, we have to take that up next time though, okay? All right, so finish your homework. We're out of time for today, but we made good progress today. So I hope y'all were paying attention and followed sort of what we did, because that's really what we did there is really how calculus works, all right? So I will see y'all again on Thursday. Make sure to finish your homeworks that are due, right? And go to the review session tomorrow with Madison from 12 to 2. I'm going to turn off the tape now, but if y'all have other, if I can get this thing to come up, if y'all have other questions, of course you